Oh, oh, oh.
Okay, everyone. Welcome back. So this is the beginning of this afternoon session. So we have Pierre Lecomte with the SPAT box. I think his presentation is going to be slightly shorter so that you guys can go try the system upstairs. Then we'll have to come back here for the next workshop. Okay. Again, there is going to be a break, and after the break, there is going to be 2 parallel sessions. You're going to have to choose if you want to do Faust or if you want to do the other things. Okay, cool. Pierre.
Okay, hi everyone. So my name is Pierre, and I will present to you today a project I've been working on for a few months now, which is called the SPAT box. So, which is a project to specialize sounds from an hardware interface. So the idea here is like, as we told this morning with the Tommy presentation, like 3D sound is widespread nowadays. So music, cinema, concert, game, virtual reality, and so on. And you have an important offer to create immersive sound content. But often I think I miss some hardware tool to play with and to specialize sounds with just a few loudspeakers to offer the ordinary musician in his room to play with a few loudspeakers and to play with sound in space. That's the idea of this project. I was looking to design an autonomous hardware interface to specialize sound in real time by just turning minimum knobs. That's the idea. And I should plug my instrument in it and then output the loudspeaker signals. And I have no more things to think. Should be very cheap for the ordinary musician, like a few €100. And my goal is to play live music with it, just to, not to compose, but just to play live music. What I did was to use Faust, as I usually do, and put that on an embedded system. And I went with a Raspberry Pi, which offers me with a multi-channel audio at 6 inputs and 8 outputs. And inside, the engine will be run with ambisonics. And so the SPAT box, what it is, right at the moment, it's an hardware interface, so knobs. Those knobs value are read by a Python wrapper written for the Raspberry Pi, which drives a trajectory engine, which I will present just in the next slide. So this trajectory engine can be used locally on the machine itself, or to drive remotely another audio engine, 3D audio engine. If you can afford like a big system with many loudspeakers, you still can use the SPAT box trajectory engine to drive your system. And the spatial audio engine can as well be local in the machine for 8 loudspeakers maximum in this case, or remotely as well. And we'll have a problem to see your trajectories. For me, it's really important because just hearing it is kind of hard, especially if you have just a few numbers of loudspeakers. So there is a remote trajectory engine, which my goal would be to have it on the phone, on your mobile phone. So far, it's on a computer. And so the communication between all these blocks is like that. So the hardware interface provides communicate with I2C bus on the Raspberry Pi. There is some Python code which handle all those value and send them through OSC. So there you can send it locally or remotely. And here you have your trajectory engine, which describes the trajectory of the sources, which drives the 3D audio engine, which inputs audio and outputs audio. And the trajectory parameters can be sent to a visualizer. So the trajectory engine, the approach I chose is to use parametric trajectory so that you can generate a multitude of trajectory just by turning a few parameters. And I went to describe the coordinate system over time with some functions. That's the idea. So either the Cartesian coordinate, if you want to front, back, left, right, up, down, or spherical, if you want the distance and angle from your point of view. So both coordinate systems are available. And you can pass from one to the other with those mathematical formula. And the idea is which functions to choose to drive those coordinates over time. And I went with a very common thing in audio, which is low frequency oscillators that so any people working with synthesizer should know. And depending on the waveform you're using, the frequency, the amplitude, and the phase relationship between your oscillator, you can start describing trajectory. Exactly when you're running an oscilloscope and you plot y over x and you can see some patterns, that's the idea here. But you have z as well. So far I have 6 waveforms available from sine, sawtooth, or even square or noise. And some examples of trajectory. For instance, if I would like to have a circle, I could start with a sine oscillator on the x coordinate. And if I run a sine oscillator on the y coordinate exactly with the same parameters, I'm going to have a diagonal oscillation. But now if I just put out of phase the sine to be a cosine, in fact, I will start having a circle. And if now I add a sawtooth oscillator on the z frequency, I will start having an helix, which starts again and again. And by changing, for instance, the amplitude of the y or x, I can describe an ellipse and not a circle anymore, and so on. So just by turning a few knobs, you can move your source around. And for instance, this flower-shaped trajectory would be done with a sine oscillator on the radius coordinate, if I choose the spherical coordinate system. So the source is going closer and further over time. At the same time, I put a sawtooth on the azimuth, so it's turning on azimuth, while it's going further, and so you describe this flower. Now if I put, for instance, a sawtooth instead of a sine, I will have some gear-shaped trajectories, and so on. So that's the idea of the trajectory engine. And so the spatial audio engine now is provided by MB Tools, so some tools have been written with FOST for a few years now. And because it's in FOST, you can have many output format. So you can drive a remote system, or you can put the code on the Raspberry Pi or on whatever you want. And so far I have some encoders, some decoders. I have binaural decoder and spatial audio effects, which I will so the next step for the SPATbox is to insert some effects between encoding and decoding. It's already on the machine, as you will see, but the knobs are not working yet. And so the features right now at this moment of the project is like on the interface, you can have the coordinate system you can choose with a selector. You have a Doppler effect if you want, because when your source is moving, you can have this pitch shifting effect, so the Doppler effect. You have some knobs to scale and the trajectory by multiplying by a factor all the LFO at the same time. So your circle will be big, and you can play with that. You have a speed as well. So far the speed is you can have an internal clock system, or you can synchronize with MIDI from an outside instrument. You have hold and reset functions that you can press a button and the trajectory just hold in place, so you freeze your mix. Reset, all the sources start again from the start of the trajectory. You have those knobs, translation and rotation. from your point of view, you can just move the wall trajectory away or rotate it around you if you want, both at the same time. You have this mode, all source at once, which when you turn one knob, it applies to all the source at once, for instance, speed, scale, or you change one LFO. Since yesterday, you can have a trajectory preset loading and saving. So I hope you will play around and design me a very nice trajectory and you save them that I can play after with them. And so you have two mode of use, standalone use that you will see today on the demo. So 6 inputs and 8 outputs. So Ambisonic's order is maximum, it's 2 in this demo. And if you go for the remote system control, then it's your system the limit. All right, so finally a picture of the gear itself. That was 2 weeks ago. and today, hopefully it's working. And yep, so it's upstairs, and I hope you'll come and try it and give me feedback to see. I hope it will be a tool which can be used for a musician to play with 3D sounds. That's the idea here. So thank you for your attention, and if you have any questions, I'm happy to answer to it.
So what I would suggest is that we all go upstairs to check it out. We have to be back here at 1 sharp, okay? Sorry, at 3 sharp, okay?
You mean everyone goes for the Spatbox demo right now?
Yeah, that.
Okay.
Well, that's what you said. No, I think it's
No, if you
possible.
want.
I think we have, we have 10 minutes. I think it's probably a good time to do it, right? So
Yeah, but okay.
Okay.
Why not?
field trip.
this over here. So, yeah, I'll tell you when I'm going to plug in. Yeah, all right. Okay, yeah, ready to go? Hi again. Right, so over the next 55 minutes or so, this is going to be about FPGAs and open source FPGA tool chains. And the kind of aim of this workshop is to, well, by the end of it, you should be able to take a kind of basic, affordable, cheap FPGA and turn it into a synthesizer. And also, we're going to look at a method of sound synthesis which is very amenable to running on these sorts of platforms. So that's the aim. It's going to be split. About half of it I'll kind of talk through about the open source tool chain and how it works and how we can make a really basic synth. And then we'll look at this method of synthesis called ByteBeat, which uses logic functions, and you can try that in a web browser online using a live coding system. So we'll kind of split it into a walkthrough and then some practical stuff after. I think I just said all that. All right, so FPGAs, we've had a lot of talk about them already today. So just to reiterate, field programmable gate arrays, these are programmable hardware. They're quite useful for music because they're really super powerful and parallelizable and high frequency. So we can run some very powerful DSP processors on them. There's lots of interesting potential there. We've got this basic unit of computing. So we've kind of got the native resources of the FPGA, which is a lookup table. And so by programming an FPGA, we just configure how these lookup tables relate to each other and what transfer functions they have. In addition to lookup tables, we might have some memory, probably a very limited supply of memory, and we might have things like multipliers, or if we're lucky, stuff that does signal processing for us. These things tend to run very low power and very high speed. So the boards I'm going to talk about today, I'm going to talk about the open source version. So I've got one of these things here. This is a lattice development board. They cost about 40, 50 pounds, I guess, or they used to at least, maybe not now. And you can get cheaper versions of these. There's one called the Iceworks, which costs about the same as a Teensy. So they're kind of in that bracket of affordable, hobbyist sort of tech, although quite different to the microcontrollers. So how do we program these things? So we program Arduinos and Teensys, usually with C, maybe Micro, Python or something like that. Of course, we've seen we can program FPGAs with Faust, so we've got some high-level tools that are kind of for specific purposes. The more general purpose stuff, we tend to go into something called hardware definition languages, and the two popular main ones are called VHDL and Verilog. So what's the difference between conventional programming languages and these hardware definition languages? Well, in a conventional programming language, we have a sequence of instructions which turns into assembly language, which gets fed through your CPU, and your CPU follows those instructions. In FPGAs, we don't have a CPU. We don't have anything really. It's just the basic kind of computing resources of logic gates, which you could actually build a CPU on an FPGA. So these hardware definition languages, they describe how you configure the lookup tables on the FPGA and how they connect to each other in order to make what you need to make. So it's a bit more like when you save a max patch to text, it describes how all the units connect together. So when we're programming in these hardware definition languages, it's more like kind of description of a circuit than a sequence of instructions in some cases. In some cases, it looks like a normal programming language as well, which is why it gets quite confusing actually. If you're moving from, say, being a C++ programmer into using Verilog, there's lots of parallels which tend to get a little bit confusing. So FPGA is an open source. FPGAs have been around roughly since the mid-80s. So Xilinx, or in their kind of current recognizable format, Xilinx did the first ones of those. But it's taken until 2015 for open source tools to appear. And I don't really know why that is, but that's how it happened. So there's something called Project Ice Storm, made by someone called Clifford Wolf. And what he did is he took this chip here, the Lattice Ice 40, and he reverse engineered, or he and his team, reverse engineered the bit stream that gets produced when you configure the FPGA, and kind of worked out how to build a compiler for it. And so since then, this stuff has taken off quite a lot, and there's now something called F4PGA, which used to be called SymbiFlow, which is a kind of collection of open source utilities, and it only targets some very specific hardware, and maybe that's because some manufacturers really like to keep their stuff confidential for various reasons. And so Xilinx 7 series, which I believe Faust might be using. Is that correct? Yeah. Yeah. So you can get Project X-Ray. Will do some open source tools for that. And then you've got a couple of Lattice chips. Lattice are quite a small FPGA manufacturer in comparison to people like Xilinx. And then you've got some newer GoWin FPGAs, which seem quite cheap as well. I think they had a kind of $5 FPGA or something like that. That was quite kind of small FPGA, but it makes these things accessible and affordable for hobbyists and artists, which is great. And so what Ice Storm has led into is this thing called Yosis, which it's on GitHub. And what this is a collection of utilities which let you take some of these hardware boards that it'll interact with and write software, but configure them to do computing, because I think writing software is probably the wrong way to describe it. And so what I'll do is just show you an example of how this stuff works to make a really basic synthesizer with one of these boards, and then we'll go through and try the synthesis technique ourselves. So this is the Lattice chip. This is the dev board that Lattice themselves makes. I think that the chips themselves are much cheaper than the dev board. They're probably $5 or $10 or something like that. Used to be, yeah. So everything's gone up in price at the moment for unfortunate reasons. So what can we do with this chip, and how does that relate to how we think about making sounds? So this chip has got 8,000 logic gates on it, which you can configure to do what you want. And it's not a huge amount in FPGA terms. Some of the more expensive ones can have 100,000 or much more than that. But for a cheap FPGA, that's pretty good. It's got 2 PLLs, phase-locked loops, and what they do is allow us to make clocks that are different clock rates than the system clock. The system clock runs at 12 megahertz. You can use these PLLs to get clocks 10 times that if you like. It's got a bunch of RAM blocks that total up to about 16K, so it's really, really low memory, even compared to some of the very small microcontrollers. And so basically, it's really basic. It's kind of native computing resources that you need to put quite a lot of work into figuring out how to configure to make sounds. So what does this all mean in terms of sounds? Well, within these resources, if we take some kind of classic methods of synthesis, well, if we're going to do something sample-based, we could do something with wavetables, maybe. You could fit some wavetables into 16K. There's nothing to stop you soldering a RAM chip onto these boards. That's a different level of complexity as well. We could do FM pretty well with it. We could get some sine wave tables and do FM or PM synthesis. Virtual analog, well, it doesn't have a floating point unit, but we can simulate that. We can use fixed point. That'll take up a whole load of resources though, but you can do some sort of virtual analog kind of traditional floating point DSP on them up to a point, but it will fill up pretty quickly. Physical modeling, we could probably do that as well because it's very parallelizable. I don't know how much would fit onto these small boards. Or there's other forms of synthesis which we can try out as well, and we're going to look at one of those. So first of all, let's have a look at this tool chain. So if I go into, actually maybe it's good to talk about through this DAC first. So what I will show you is how to make a really cheap DAC for FPGAs. So we don't need to add a sound card onto them. We can just, or a DAC chip separately. We can just use the FPGA itself using something called pulse density modulation. So how does this work? What we do is we take a waveform and we quantize it into zeros and ones. And as you can imagine, that potentially that could sound really awful, but if you do it at a really high frequency, you can get a really high quality signal. So I'm just going to defer to a different paper on this for a very nice example of how this works as a visual analogy. So this is a paper called Understanding PDM Digital Audio. And the visual analogy here, so on the left we've got a grayscale image, and in the middle here, this image has been thresholded into black and white, ones and zeros. And it doesn't look very good. So we've lost all the subtleties out of the image. This image on the right is still actually made out of black and white, or just black dots. But what's happened is these dots have been distributed according to the grayscale of the image. So we've turned it into a binary image. There's no kind of gray, there's no gray in this image, it's all just black dots, but they're distributed in a particular way that gives the impression of gray. So in PDM, we do a very similar thing. We take a waveform and we run it through some processing that generates a stream of pulses at a much higher frequency than the original waveform. And when we listen to those, they give us the impression of the original waveform. And what's nice about that is you can do that with a digital pin. So you don't need anything special other than a filter. So you put a low-pass filter on the end, and which kind of averages out all the pulses back into the original waveform. So the circuit for that is, just find the slides. So very simply this. So we've got a low-pass filter here, RC filter. You can tune that to whatever frequency you like. We've got a coupling capacitor, and that's it. So on this FPGA here, so the sound card is literally a bit of stuff soldered into the socket, and it's attached to a digital pin. So it's all very simple to get a DAC to do that.
Chris, can I just say one thing? So if you're having troubles to see the slides, because it's pretty bright, we need to keep the lights like this, because otherwise people remotely, they can't really see anything in the room. What I would suggest maybe is if you have your computer, like you can go to the live stream where there is actually the slides being in HD, but it's just that it's very, very small here, and it's very bright, so it's kind of hard to see what's.
I think I might be able to flip the theme actually.
Just a suggestion.
Yeah. If you can put a light theme, it would be.
Yeah. I think that might work. Yeah. So this is the Verilog code for the DAC, and I'm not going to explain all this, but the main point is it's a very simple, small bit of code. It's only a few lines of code. So we run an accumulator at a very high frequency. Every time it overflows, we output a spike, and that kind of gets added into this pulse train of PDM. We have to run this at a high frequency. So there's no strict rule of how fast you could run it, but people say roughly 64 times higher than the original frequency, which on a normal computer would be really complicated, but on an FPGA, that's fine. So on this one that I'm going to show you, I've just tacked onto a clock that was already running. So it's running at kind of 2,000 times oversampling. It doesn't need to be, but it seems to work fine. So yeah, I was going to kind of show you this tool chain as well. So Yosis is a bunch of command line utilities, and you can grab it from their GitHub. It used to be a bit complicated to install, but now they've just got a bunch of binaries that you can download, which makes things really easy, and it installs a bunch of stuff in your path on your computer. And it's pretty much simple as having a make file. So I could show you a bit of, we can kind of move into looking at some synthesis stuff. If I just shift over to a different workspace. So I can talk through the kind of rough architecture of how you turn one of these boards into a very simple synth. So this is all Verilog, but I can kind of explain roughly what's going on. So basically we specify a master clock for the system, and then I've got something which is an audio engine which divides that clock down to 44.1 kilohertz. It doesn't have to be that actually, it could be anything really. And I've got a bunch of code which runs which looks like logic statements, which is what's making some sounds here. So this is the type of synthesis called byte beat, which we can have a look at. And then we send a signal to a DAC, and this is the DAC that I just showed you. So it's all fairly straightforward to make a sound. In Yosis, we just have a make file. So if I just change something here to make sure it compiles.
Chris?
Yeah.
Can you zoom in? Because
Yeah,
really,
sure.
really, really tough.
How about that? Is that? Yeah. So this was, when we make, so on conventional computers we compile, so we take our code and it turns it into assembly language. On the FPGA, what we do is we take our Verilog hardware description, and it gets turned into a bunch of logic gates and how they connect to each other. So that's step one. And once it's done that, it gets put through something called a place and route, which is an optimization process which tries to fit all those logic gates onto the hardware of your FPGA in the most optimal way. And I think it uses things like simulated annealing. So it's a kind of a discrete optimization process that figures out different combinations until you get an optimal circuit. So when I typed make there, it did all that sort of stuff. If we go up a bit, we get a report of how much resources it used on the FPGA. So to make a sound, I've used about 1/16 of my FPGA there, or maybe 5%. And it gives you some kind of timing report to tell you how fast you can run this and if it's safe to run at that particular speed. And then the next step is I burn it to the FPGA. So if I just do that, then it flashes it all to the FPGA. And if I plug it in, this might be a bit loud because it doesn't have a volume control. Then let's see. I think. Oh, it doesn't have a volume, so. Oh yeah. If you could turn it up a little bit, actually. Yeah. So, doing something there. Okay. Thanks. I think I've got a loose connection. So let's talk about this sort of synthesis then. So, like I said, doing kind of conventional synthesis in FPGAs, we might end up using a lot of resources. About kind of 10, 12 years ago, someone called Visnut online came up with this form of synthesis called byte beat, which basically allows you to use logic statements to make sound. in a kind of quite a chiptune home computing sort of way. But it's really interesting to experiment with. So all these logic statements that you see here, we're basically taking integers, doing lots of kind of bit shifting, logic functions. And what we do is we have a time that counts up from whenever you turn the board on. And it's like functional rendering. You take the time and you make sound as a function of time using bitwise arithmetic and integers. And that's really amenable to FPGAs because it doesn't take up much resources. You can run this stuff with practically no latency. You don't need any complex things like floating point units. You don't need many arithmetic logic units and so on. So we can have a look at this form of synthesis. So what I will be showing you is something like this. This is a live coding system called SEMA, and it has a language called Nibble in that, which we can all have a try at. But first of all, I'll just talk you through the principles of this synthesis method. So this might be it's a bit hacky, but let's have a go. So what we can do is we can take a number and just get it to count up forever. And that could be an 8-bit number, it can be a 32-bit number. Maybe having lots of bits is good because it will take longer before you reach the max and have to loop back again. And as we count up that number, we can observe and change bits of that number and transform them into waveforms. And by doing so, we can make sound. So let's have a look at a really basic, this is a binary number that's counting up, as shown in binary. And let's have a look at the bits here. If we look at a bit in a particular position, we can see that the bit is actually an oscillator. It's a square wave. So if we look vertically, if we look at the 0th bit of this number, it's a square wave going up and down, up and down. If we go along a bit and maybe look at the 5th or the 3rd bit, we can see it's also a square wave, but it's just slower. So it's taking 4 counts off, 4 counts on, and so on. And we can go all the way along a binary number and pick out square wave oscillators just by looking at a fixed bit. So immediately, for free, just by counting up and taking one of these bits and sending it to the DAC, we've got a bunch of square wave oscillators running at different frequencies. And of course, this is it's not very flexible because all the frequencies it's all in octaves. It's double each other. So that's not great, but there's ways around that. And we can do other interesting things like, so supposing I take this time and say I AND it with the number 255. So this would give us a saw wave, so we can kind of see a pattern going up in a ramp there. Now let's have a look at this in practice, and then you can go and try this making it yourself. So this is something called SEMA, which we've built at the University of Sussex on a AHRC funded project to explore different ways of live coding that incorporated machine learning as well. There isn't machine learning in this system here. And what it lets you do is design your own language. So we don't need to get into this, but this is the grammar for this language. So you can go and, it's got an audio engine and grammars that let you connect with the audio engine. And so with this is a byte beat language. Shall I just try and expand that a little better? And so let's try what I was just doing. So in this language, we've got this time, which is t. So this is an integer, 32-bit number, which is just rising all the time. I don't know how long it takes to get to 2 to the 32, probably quite a long time. And if we do t and 256, what I'm doing is I'm picking out the 9th bit of that number, which is going to be a square wave. And then if I shift that up a little bit, then we should be able to hear that on the DAC. So I'm just going to probe. Oh yeah, I'm just going to plug this laptop into the sounds. So if I run that, so then I get a square wave. I can make that square wave quieter just by shifting it to the left a little bit less. I can change the characteristics of the wave by fiddling around with this number here. You can get kind of different waveforms. Or we can do things more complicated, like the code that was originally here. So you can start to make more complicated things build up. So for the last 20 minutes, what I suggest is we could try out this bytebeat language. So this is online. You can go to nibble.sema.luma.net and so maybe what we can do is just run through the first few steps, and then there is some help on there. So if you type Alt-M on here, then you get a bunch of help, and there's some tutorials on how, with some examples that you can try out, with a bunch of kind of different statements which you can go and cut and paste into the editor. So if you're listening on YouTube as well, you should be able to try this out at home. So you can just take these, paste them in, and see what happens. So it all sounds very 80s home computing, but that's kind of the fun of this language. Some of it's really quite indecipherable. It's because it's quite complicated, it's not always clear why a particular thing works and why a thing doesn't. So I suggest just going and trying it out and experimenting. So maybe if I leave this URL here, maybe we could go and kind of run through the basics, and then maybe in the last 5 minutes, if anyone's got a kind of really nice thing they want to play out loud or something like that, we can try that. So has everyone got a laptop? Oh, okay. Well, maybe you can work in groups if you don't have a laptop. It won't work on a phone, I'm afraid. But maybe you could do kind of work in pairs or groups if you haven't got a laptop.
Did you say you open the documentation?
So if you go here and you click on the question mark, it shows you the instructions, which look bad because I've zoomed in my browser. But yeah, but basically Alt-M. It's quite a hacky interface. And while we're getting into that, has anyone got any questions about the open source stuff as well?
Is it also possible to put an input on this kind of GA system?
Yeah, that's a really good question. So in theory, the principle that I showed you for the DAC with a slightly more complex circuit should work for the ADC. I haven't tried it yet, but I've got Lattice have published a guide to doing so. And so you need a couple of RC filters, and there's something special called an LVDS input, which is a comparator, which lets you take some of the hard work out of the ADC. So in theory, it's possible, but I don't know. And also in general with these DACs and ADCs, I haven't done any formal measurement on them, so I don't know how many effective bits I'm getting out of it. Apparently, according to my Verilog, it's a 32-bit DAC, but whether it's actually 32-bit in effect or not is another question. Yeah, so yes, but who knows the quality, I think.
Max about 10 bits.
Yeah, okay, so you've done that?
Yeah.
Yeah, okay.
It mostly has to do with the quality of your comparator.
Yeah, okay. So you use the comparators on the LVDS?
I've tried that and I've tried external comparators as well.
Yeah, okay, as well. Yeah. Yeah, so could you use 10 bits for sound? Well, I guess so. I mean, will it run at high frequency when you do that?
Yeah. Not really.
No?
Yeah, I haven't had a bit, because there's that Lattice white paper and there's also an old Xilinx one.
Mm.
I've messed about a bit with both of them, and I think you could have more luck if you use external higher quality comparators,
Yeah.
but yeah, because it's a hybrid process, so your filter matters, so that's your comparator, so it's your drive stage,
Mm.
and all of these change depending on which FPGA you're talking about.
Yeah.
Because within any sort of ADC like that, you're also creating a DAC,
Mm.
and the DAC
That's
takes
right.
time, and the quality of the DAC
Mm.
matters. If you want a higher quality ADC like that, sticking a delta sigma DAC within the loop is maybe not the answer. You might want to go with some sort of a flash DAC or something that's faster and higher quality.
Mm. I see. I suppose the dream with these is that you could really easily kind of, if you can make a DAC and ADC, really think, okay, well I can easily make an in 8-out sound card without much external electronics, and I guess you can do that at a low quality. But
Totally can do it.
yeah, I mean the DAC seems reasonable to me, pretty good actually.
The DAC looks great.
Yeah, yeah.
So, yeah, at the beginning, I'm not sure I understood. So, this particular lattice FPGA was reverse engineering.
Mm.
So, they built this compiler for this FPGA. But it means that, so I knew somebody who did that in Brittany a long time ago, but the problem is that it has to reverse engineer every generation going out of lattice, or is lattice going to see what I mean? You are stuck to
Yeah.
this particular lattice FPGA, and if there is a new FPGA, you cannot use.
Yeah, I don't know if it. So that they list all the ICE40, particular ICE40 chips, which come in lots of variations, and they list the ones that it works with, and I think they've adapted it for another one called the ECP5, which you're using, right?
My question is, how is it seen from lattice?
Yeah, I know there was some politics, but I'm not quite. I think it happened independently from Lattice, and I guess they tolerated it because they didn't kind of get their lawyers to shut down the project or something.
But did not either give them their new or bitstream format for new
Sorry, can you repeat that? Oh yeah.
I was just wondering whether there is a hope to have at some point a collaboration between FPGA vendors and open source compiler guys who could provide this kind of tools, but
Yeah.
currently it's just they reverse engineer the bit stream
Yeah,
and then they provide the tools.
As far as I know, they reverse engineered independently, and then, so I don't know if the open source community has a relationship with Lattice or not. I'm not sure if they do, but I guess Lattice have tolerated the open source
Yeah.
because they could have legally done something about it, I guess.
I had another question. So the synthesis seems very fast.
Mm-hmm.
So is it because it's a small FPGA, or it's because it's not optimized, or what do you think?
Oh, you mean, yeah, so that synthesized in a few seconds, right?
Yeah.
I think in this particular case, if you look at the Verilog, this is quite simple in Verilog terms. It's not using any memory. It's not using, well, it might be using the multipliers, but it's not pulling on extra resources. And I think there's just 2 clocks in the system. So as far as compiling goes, it looks straight. It's just LUTs used simply. So I don't think it's having a hard time. And it only used about, 500 out of 8,000 of the gates for this one. I think it takes exponentially more time to synthesize. So maybe for a small thing like this, it's just really quick. I've been paying attention to this because the reason I got into these, I was using them for live coding. So I used to have this thing called DJ FPGA, where there's 2 FPGAs, and I'd code one, and they're plugged into a DJ mixer, and then I'd code the other one, and I'd crossfade them. So kind of live coding with hardware, which is kind of how I started exploring this. And so I developed methods that you could do in performance time, basically. So I had to find stuff that compiled in 10 seconds, otherwise it wasn't going to really work. So I don't know, if there's no more questions about the open source stuff, we could just spend the rest of it trying out the byte-beat language, maybe, if anyone wants to do that. But some of you haven't got laptops, which is a bit tricky, I guess. Yeah, I don't know. What do you think, Ramon? Yeah. Yeah.
Yeah, what I would suggest is that you guys can try this. You know, like we're supposed to have a coffee break after this presentation, so you know, like you can have an early coffee break if you want to go check the installations upstairs. That's another option. You know, like and basically at 4:30, yeah, 4:30 we'll resume with one session here, and we're going to start with Maxime and Pierre, who will be giving a workshop on FPGAs again. And in parallel with that, there is going to be a 2 hours Faust workshop happening in the very colorful room in the entrance of the building. Okay, so you have to choose. It's either at 4:30 you come back here, or you go to the Faust thing. Okay. But in the meantime, until 4:30, you can either just check Nibble and ask questions to Chris, or go check the installations upstairs and maybe just have a break and talk to each other. So yeah.
Yeah, can I just point out that for our workshop, which is happening at 5:30, one will need a laptop if you want to be part of it interactively. I mean, you can sit and watch and listen. But the fun part is to actually make some noise.
So bring your laptop. Okay, and of course, if you have questions for Chris, there is plenty of time to ask them. So yeah.
All right. Okay. All right. Oh, could you yeah, that is. Yeah.
No, well, yeah, I think we can. Well, I guess, yeah, there is a...
I could.
Yeah, there is a question in the chat, and the question is, I'm not sure, but I think this morning you mentioned PDM being one of the possible use cases of ML for music. Could you tell us how?
Yeah. What I could do is reply with a couple of papers in the YouTube chat. Maybe that's the easiest thing.
Yeah, maybe,
Is that on the YouTube chat?
Yeah, yeah.
Okay. Okay, cool.
It's a French keyboard.
Yeah. Actually, I'll reply from mine because
Yeah, maybe
I've got
it's
the
easier,
links. Yeah.
Okay, so Thomas, Chris will reply to you directly in the chat.
Oh là là. Quel niveau de code est lisible? Moi, si niveau taille de police, là, c'est acceptable ou faut plus?
Il faut que ce soit plus gros.
Oh merde. Ah.
Là, ça va, oui, là,
Ils n'ont pas trop besoin de lire, ils ont juste besoin vite fait de comprendre.
C'est limite, mais ça va.
Je suis pas sûr. Est-ce que le son est activé sur le streaming? C'est ça la question.
Du coup, ce que tu voulais, c'était que l'écran prenne tout à l'heure.
Non, c'est juste que j'avais un. En gros, moi j'ai un truc sur mon écran et le rétro me servait de deuxième écran. Tu vois, il n'y avait pas la même chose qui était affichée. Et je voulais que ça affiche la même chose parce que autant quand je fais ma présentation, je veux pas qu'il y ait la même chose. Mais là, je veux qu'il y ait la même chose que. Tout à l'heure, quand je faisais ma présentation, pour le coup, je voulais qu'il y ait mes notes sur. Enfin, je vais pas avoir mes notes. Il y avait juste un chrono que d'ailleurs Stéphane m'a complètement pourri. En fait, au bout de 5 minutes, et Stéphane me dit il reste 5 minutes. Puis, du coup, je lui fais un regard insistant, genre non, ouais. Et je dis non, il dit si. Non, il me semble vraiment pas, moi j'ai mon chrono. Et en fait, il me restait un quart d'heure. Et du coup, j'ai un peu speedé. Puis, moi, je me suis dit bon, il a plus l'air de trop me faire chier, donc je pense qu'il s'est rendu compte que c'était pas bon.
Et t'as pas pu.
Bah non, mais c'est juste qu'il me faisait des signes, puis c'était un peu genre non, c'est pas bon. Je pense qu'il s'est planté de 10 minutes. Et surtout que j'étais complètement perdu. Que je dis, alors, finir mes 15 minutes en 5 minutes, va falloir rusher là quand même. Ouais. Faut aller très vite. Ouais. Putain, je vais essayer de faire un truc pas trop décousu, mais. Ils vont pas aimer s'ils voient du code.
Okay, everybody. So we're going to start the final session for this afternoon. So in this room, we're going to have 2 workshops. The first one is going to start now, 4:30. It's going to run until 5:30. The next one is going to be from 5:30 till 6:30. Okay. If you want to go to the Faust workshop, you should go to the room, which is in the lobby, okay? And so it's your decision, you know, like it's either you come here or you go to the other workshop. So this first workshop is going to be about the work that Maxime presented this morning on programming FPGAs with Faust, okay? And then the next workshop will be a Bella workshop, okay? Great. So now Pierre and Maxime will give their workshop. Thank you.
We good? On va, c'est parti. Okay, so thank you everyone. Thanks to come to our workshop. During this hour, we will be presenting the Cifala compiler. So I'm with Pierre Cochard, which is an engineer on the project, and he is the engineer who writes basically the Cifala compiler, the command script and everything. Yeah. So I have to repeat a little bit about my presentation this morning to be sure that everyone understands how the Cifala compiler works, and I will go a little bit more into the details. And after that, we will see the command line, and we will really use the Cifala compiler. There is so you have to know that to use the Cifala compiler and to program an FPGA, you have to use the tools that provide the manufacturer, at least for non-open source FPGA. I don't know for open source FPGAs. But if you use an Xilinx FPGA, you have to use the Xilinx tools. Those are pretty big software. It's requires that maybe 100 gigabytes to install. So it's huge. It takes us maybe an afternoon to install because it takes a long time to install. So I suppose no one in this room have the Xilinx tool installed on the software on your computer. So it will be more show than a handoff for this workshop. Sorry for that. But Xilinx tools are free, right? You can install it for free. Because as long as you use them, Xilinx know that you're going to use the FPGA, so they just give you the software for free. So you can really install the entire Cifala toolchain for free, and you can do it on your computer. Just one thing, it's only work on Linux, right? The Cifala toolchain. So with Ubuntu and Arch, we try, and yeah, okay. So yeah. I will mostly show you what we are doing, but you can download everything. So just to come back to what I said this morning, so the big part of the compiler, of the Cifala compiler, is that we have to split the computation into two different files. So one file is going to contain the sample rate computation, and the other one, the control rate computations. So this is done by Faust, by the Faust compiler, right? And so this was this morning. Yeah, this schema is pretty important. So we will see how the Faust compiler can split into two files, and we also will see how the IP is implemented on the FPGA. Because there is another schema that I didn't show this morning, this one. So it's pretty, there is a lot of things, but it's really the implementation, the fully implementation on the FPGA. Because the idea is that you have here your Faust IP. So this is the function, the audio function that you want to program on the FPGA. But you have to implement other, let's say, driver. You have the I2S driver transceiver, which is the digital protocol that we use to communicate with the audio codec. You have to implement so this is the block RAM, but you have to implement the communication. Here the communication with the DDR. If you have some external controller, you have to implement all those driver and controller. So when you have your Faust block, your Faust hardware, you have to add some other thing. This is important because this is the big part of the project that we're going to see after. Yeah, I will come back to this schema, but this is the idea that you have to know. So how does it work? So anyone in the room know what FOST is, right? Okay, perfect. So this is pretty easy. I have to just take a console. All right. So the Cifara toolchain it's a command line. So I can write Cifara help minus help, and you can maybe you know this kind of help. So you have a lot of commands that you can use. You have example that's everything going to be shown by Pierre after. You have the possible command that you can write, and a lot of command and a lot of option, right? We will see that later, but the idea for this option is that you can tune the Cifara compiler for your project. For example, if you want a sample rate of 768 kilohertz, well, you just have to specify the option and you will compile for that. You can change the sample width, 16, 24, or 32 bits. So as I was saying this morning, right now the Cifara compiler works for 3 different boards. So the Zibo Z10 and Z20 made by Digilant, which is those little board, and the Genesis by Digilant 2. So it's this big FPGA board. It looks like that. So the FPGA is just a little thing behind the head thing here. So it's an UltraScale Plus FPGA. It's a pretty big one. This step. So yeah, you can choose the board on which you will want to implement your program. You can choose the controller. We'll see that later. The volume for the embedded audio codec, etc. So let's say I want to make a FOST program. So I will write a FOST program. So I have already a program ready, which should be here. So I think I don't have any sound, but it's okay. Yeah, I forgot I have. No, it's not this one, sorry. So, nope. Sorry for that. It's a Quran. Okay, okay, sorry. Okay, maybe. No, I really don't have any sound. So this is just a little program you have to imagine, sorry, that do a sine wave with an LFO, so you just have a sound. The idea is just to show you that you can have the sound on the FPGA, so we'll hear it later. But anyway, I want to implement this FOST program. This is the GUI that FOST generate. Okay, you don't see anything, perfect. So anyway, the FOST program isn't very important, but just to show you that there is a GUI just here, and this is the program. So the idea is that you just, so you export this program in a file, in a text file .dsp, and you can just add it in the argument of the Cifara command. So this file that I just show you is called virtual analog. And I can add some options if I want to compare it on Genesis or change anything that I just show you. I can add the option just here. And I just have to do that, and if I hit enter, it will compile it, and I come back in 15 minutes, and I will be able to program it on this board. So just to show you, I will do everything step by step. we have a command that do everything step after step, but here I will just stop at each step. Okay. So the first step, if I come back to this part, so I have my first.dsp is the file that I just show you. I need to generate two different files. So the file that will contain the computation, the sample rate computation, and the file that will contain the control rate computation. So just by doing the arch option, our scripts, well, he just called the first compiler 2 times. Okay, so you can see it here. Yeah, so my screen is too, yeah. So I called the first command just here. I just put in argument the DSP file that I write, some option, and it will generate the file that will go on the CPU, so the file that we handle the control rate computation. And I call it a second time in the same line. I think it's here this time. This is not exactly the same option. It has to be different because you don't want exactly the same two files because you won't do the same thing on the CPU and the FPGA. But it do basically the same thing. You take the same file in arguments here, just here. So some different option, and it generates the C++ file that will go onto the FPGA. So we just did this part. So right now we should have a hardware.cpp file and a software.cpp file. So if I go to the build, where it is? Right, perfect, I don't have it here. So if I do in a build file, so I have two files. I have the one, the C++ file that will go on the FPGA, and sorry for that. No. Pardon. Perfect. So those two files, first generate them. So you can see there is two important functions. If I find them, this is a pretty big file. So everything here it's first. First generates everything for the C++ file. But if I go deep inside the file, I will find it. Still not here. Oh, yes. There is two functions, a control function and a compute function. So the control function first did this dispatch. I didn't do anything. Maybe you never saw that because we work in a one sample with the one sample option because on our FPGA we don't do any buffering. So when a sample goes in, we compute it, we process it, and the sample goes out. Okay. So when you ask for the one sample option, first do those two functions. So this function here is the function that will handle every control rate computation. So all those F control are some slider and some button, as you can see here. And as you can see, it already do some computation. I have some mathematical function here. Because all those mathematical functions depend of the control, I don't need to do them on the FPGA. So I can save the FPGA resources and do them on the CPU. And so this function is the real computation, the sample rate computation that needs to be done at the sample rate. So all this function is what force generates from the DSP files that you just see before. The thing is, so the cfala application.cpp file, so this file that you see is the file that's is the software.cpp. So it's the one that's gonna be executed on the ARM. And if I take the hardware.cpp file, so for me it's called cfala ip.cpp. Well, I have the same thing. It's a little bit shorter because we didn't put exactly the same option in the first compiler. But as you can see, I also have my control function and my compute function. So the only difference is that we only call the control function on the ARM and we only call the compute function on the FPGA. Okay, so both do pretty the same thing, but just we just don't call the same function. And the way that we choose to call the right function is because we work with architecture files. So I don't know if you know the way that the FOSS compiler works, but when you compile for a specific language, you have to add an architecture file. You can add an architecture file, which is, let's say, a function that will go around what FOSS compile. So I can show you. I don't have any. Okay. This is the architecture file that will run on the FPGA. So this is my function. This is the Cifala function is what is going to be transformed to the IP, the block, the physical block that you just saw. So this is my function, and as you can see, I called the FOSS function. I called the compute function, but I never called the control function. So this is the code that you write. And on an FPGA, I only call the compute function. If I take the same architecture file for the CPU, the ARM, this is my function, and I only call the control function. I never call the compute function. So this is basically, this is the code that we write, and we just call some FOSS function, and FOSS we will handle the computation, the way that it transforms the DSP to a C++ file. So if I come back to there, we are right now on this part. We have those two files. So the C++ file that will be executed on the ARM, it's pretty much done. We have the C++ file. We just have to do a GCC command, and we have the executable. So we don't have anything more to do on this part. The other part will be the high-level synthesis tool and the implementation of the IP in the FPGA. So if I go back to my console, so now I can write Cifala. Yeah, I don't know So right now we use the high-level synthesis tool. So it takes 1 or 2 minutes, and so the high-level synthesis tool will take the Cifala application C++ file and transform it to a VHDL file. We could ask for Verilog. The VHDL files that I write aren't, you can read them, you can open them, but I can show you, but there is nothing to see. It's impossible to understand anything that is right on it. You cannot modify them because it's auto-generated, and I mean, there is nothing to tune. If you use the HLS, they just auto-generate some files, and you will take them and implement them, but once you do that, you cannot modify them. Right. So yeah. All right. So now the IP is create. So if I go there, go to check my IP. And I have the VHDL of my function. So if I go there, oops, sorry. So this is the file that the high-level synthesis tool generates. Yeah, as you can see, it's a lot of signals, and yeah, this is pretty impossible to debug or do anything. It should work like that. You won't change anything on this code. So now we have our IP. So we have to implement it. So right now we have our two blocks. We have the gray one, it's the IP that I just showed you, and the red one is the executable, where I still didn't write the GCC command line, but we almost have it. So now the last part and the longest part is to do all the implementation, so the synthesis and the implementation on the FPGA. I won't do it because it takes a long time. What I should do right now is project, and so the project will just create the Vivado project. It takes like 2 minutes. It's just configure a project with the right board because you're supposed to enter the right board, and it's just load the block design, so the things I'm gonna show to you just after that. Well, I can already did another project. So. So now I'm going to show you the block design. So the implementation that is going to be synthesized onto the FPGA. And you basically, you are going to see the same thing, but the way that Vivado needs to see it. So with a real driver and real block, real FPGA, VHDL block. Okay, so. No. Great. So, I'm gonna zoom in after, but this is all the everything that is implemented on the FPGA. So this block here is the IP that you just generate with a high-level synthesis tool. But as you can see, there is a lot of things around it. So it's not very complex block. So this one is pretty complex. It's a I2S transceiver, so it's the block that does the communication between the digital signal that goes to the codec and the signal that we compute on the IP. And the other are just, there is some GPIO handler. This is the ARM, the CPU, so you can configure it, you can add some driver and do whatever you want. All this block are some interconnects, so it's Xilinx proprietary bus that allow you to interconnect, for example, the CPU and the FPGA. So you can communicate from the CPU with the FPGA. There is some reset handler. Some clock wizard, which is pretty nice because you can generate any clock at any frequency that you want from an external one. You have some PLL and MCMM that allow you to overclock from one slow clock. And you have all your external interface. So this block is auto-generated by Cifala. You don't have to wire anything. And this is what is going to be implemented on the FPGA. But each block are VHDL. For example, if I open this one and I go to source, you have the I2S transceiver that we write that I cannot zoom. Classic. No. Sorry, you'll have to trust me, but it's some VHDL code. We write this one, so it's the I2S transceiver. So every block that you can see on it is VHDL code. Some of them we didn't write. It's Xilinx give them to you, but it's all VHDL block, because if you write everything in one VHDL program, it will be impossible to understand. So you just write some block and you wire them, and then you can have your very complex program. And so once you've done that, so this is the big part, I have to synthesize and to implement it on the FPGA. So now it's just Vivado, so it's a Xilinx tool that will do that for me. Again, I won't do it because it will ask 15 minutes, but I just have to do that, and then I will have my fully done implementation on my FPGA. At this level, I can flash my FPGA. And the only thing that I have to do now is to execute my application. So this little file, I have to execute it because an ARM is just the CPU is standalone, but you have to execute it anyway. So if I yeah, this is pretty much all. So at this step, you have everything ready, and you can just I will let Pierre show you the rest, but you don't see anything. If you just write cifala flash, you will be able to flash your FPGA with the force that you just write. We have a demo because I cannot show you more here, it's just command line. But yeah, I think I'm pretty done. If you want to show the demo.
Yeah, can you hear me? Okay. Hi, so maybe, I don't know if I should come here because I have all things settled here and I pretty much nothing to show on the screen, or at least not a lot. So maybe I'll stay here, but if you want you guys to come and see the FPGAs, the routing, the even the little interface that I made for the occasion with a quite complex synthesizer, which is an emulation of the Minimoog. So if you want you guys to come here and see for yourself and maybe toy with the synthesizer. So this is a synth made for Zibo Z20. So it's not the lowest level of Xilinx FPGA. I don't have really interesting things to show. Oh yeah.
Maybe I can compile the Minimoog and show the interface.
Yeah, you can maybe do that.
I think I have it already compiled.
All right, so maybe Maxime will explain to you better for those controllers, but these are controllers that he made actually to be directly connected to the FPGA here. So maybe it'll show you a little demo. This is the Zibo Z10, which is kind of the cheapest board we have from Xilinx. So it's made by GGLens, but has plenty of resources and computation power, I guess. This one is the Z20. It's a bit higher level. You have more resources, basically, and you have, yeah. So maybe I can show you just the Faust code.
T'as un câble micro USB pour les Zibo?
So, as you can see, if you want to go by the computer, this is the Faust code generated for this Minimoog emulation. It's quite a complex Faust code. It has plenty of oscillators and filters and LFOs and modulation. I think the code was written by Julius Smith, so it's quite complicated to read. Actually, it's going everywhere. It's really clever, and so yeah. This is the result. Maybe Maxime will show it on the screen, I don't know. But this is the result. This is the interface that is generated by Faust. And actually, we made a connection with UART, with USB, to the board, so we can just have sound.
Sorry, we just plug 16 of them.
Do we have sound here?
Yeah, it's finally working.
Yeah, okay.
2 per square, so
it's
here
really
you
low.
have 8 channel in your hand.
Oh. Can you turn it up a bit? Yeah. So you can either go through the MIDI controller, either go to the GUI interface generated by Faust, opportunity to turn the buttons here. But I've made a mapping. I don't know if you guys know Faust a bit, and you know how the mini mapping can be done directly on the sliders. But if you take a look, you can see that it's assigned MIDI controllers directly on the sliders metadata, actually. So it's a really convenient way to directly map MIDI controllers or even not-on, not-offs to a controller. And what it actually does is send the data, the MIDI data, to the computer, and the computer is going to get it through UART, USB, and send it to the FPGA. So we are not at the point that we can have MIDI directly on the board, or even OSC, but we are developing, let's say, a custom Linux for this board, well, for all the boards that we support, and we are making progress as we speak. So we probably will have a Linux running on the board with, you know, Ethernet with MIDI capabilities and OSC and everything you can think of. So yeah. So if you want to play a bit, so you have the 3 oscillators here. You can just trigger notes here and then adjust the level of the 3 different oscillators here and adjust the octaves and everything. This is the noise, so it's white, pink noise. You can select. So it's monophonic. It's going to be doing a little bit of weird things if you press 2 notes at the same time. The problem isn't really here, it's about latency more, because we use there's a lot of latency for this one, more than resource usage. So I'm not sure we can add another voice another synth voice to the board, because one is already up to the limits in terms of latency. So I think if we had another one, might not be enough time to actually process the whole computation in one sample, you know. So the latency, it's a bit complicated, because the high-level synthesis tool that we use, provided by Xilinx, does not opaque things, but it's still a bit complex. You saw the generated VHDL, so it's tried to optimize the ratio between resource usage and pretty much latency, the throughput between the inputs and the outputs. So it's a bit complicated to anticipate what's going to take up latency or resource usage, because we don't have such a great control over high-level synthesis, and also because we just run different DSP files, so it's not really optimized for one DSP file. It's tried to be optimized for I don't know, like a range of DSP files. So yeah, you can tune it by yourself if you want, by adding pragmas in the C++ code that you use for your architecture files for Faust. But it's really hard to tune, and I don't think we've maybe optimize things enough, but we are trying to make it work. So yeah. So if you have any questions or want to toy with it, feel free. Or maybe I can show you the report that is generated by this. So the high-level synthesis tool, which is going to be synthesizing the IP, so the FPGA part of the code, of the computing code, gives us some information about the latency and the resource usage, basically. So here you have the minimum cycles and the maximum cycles with the minimum latency and the maximum latency. So it's somewhere around that, depending on the cycles, I guess. And then you have the resource utilization estimates. So you can see that you have BRAM, DSP, FF, LUT, URAM, that we don't have actually. But you can see the overall utilization here and the number of available, for example, lookup tables here. We have on this board 53,000. And we have 50%, as I told you, of resource usage as for LUTs for these sims. So yeah, it's pretty valuable information because we try to optimize things depending on what we see, and we don't always see relevant information. It's always a bit blurry, I guess, on what's going to actually happen on the board. So yeah, so it's a bit of FPGA black magic. Sometimes we don't know what's going to happen, because sometimes I think we're supposed to be a bit late on the max latency, I think, but it works fine. But some of the times it doesn't work at all. So yeah, so it's a bit mysterious that way. So please, if you want to. Every move you, it's not the song, every move you make on this interface is going to be visible also on the GUI. So if you turn the filter, you see that it's moving here. So it's pretty convenient if you want to do mapping and you don't have enough knobs or sliders to do everything, so you can still control it with other means.
ça aussi que je me suis dit au bout d'une demi-heure c'est bien que ce soit fini, parce qu'une heure de ça. Ouais, non, mais c'était ultra décousu, mais. À faire des présentations. Ouais, ça je sais. Mais c'était hyper gênant en plus, je trouvais pas le truc. C'est vrai que mettre dans des diapos, c'est pas con du coup, comme ça au moins t'es sûr de.
Bah ouais, montrer du code à l'écran, c'est vraiment chaud.
Ouais, ouais.
Surtout, il faut utiliser contrôle parce que quand tu commences à faire
Ouais, je sais. Ouais, j'étais un peu. Bon, en même temps, c'est la première fois que je fais ça. Hein. Bon, je m'en fous, c'est beau, c'est pas. Et je sais pas s'il y aura des. On a fini du coup, je pense. Bon, moi ça me va, hein, mais. Moi je pense que les gens vont venir, de toute façon, globalement, visiblement.
Là, il y a notre question.
Sur internet. Ok.
Sur internet, on n'a pas.
Il y avait du monde de connecté. Enfin, je pense que pour les gars sur internet, ça a dû être chaud à suivre aussi. Ouais, bah c'est ce qu'on disait là, c'est que bon, de toute façon, ce workshop là était un peu.
Vous avez déjà vu
Hein
comment vous avez fait avec l'un en fait
Non, non, mais même de toute façon, le workshop était assez complexe. Je pense.
Non, mais peut-être.
Oui, non, je suis d'accord que pour les trucs. Ah oui, mais ça, effectivement, moi je suis d'accord aussi. Moi je te le rends du coup. Hein.
Tu penses qu'il y aura des questions des gens là?
Moi, je pense que les questions, les gens ils vont bien me les poser. Hein. Ouais.
Mais ouais, mais du coup, c'est peut-être dommage pour le live.
Ah bah, à la limite, je demande.
Garde-le, c'est pas grave. C'était au cas où j'avais pu penser aux
Mais il
questions.
marche ou pas en fait? Pas le câble.
Oui, j'ai pas, en fait, je peux pas l'éteindre de mon truc.
D'ailleurs, ça dit que les gens ont payé de la salle. Les gens ont payé de câble. Mais là, c'est pas ouf. Non, mais c'est juste que s'il y a des questions physiques que ceux d'internet vont prendre. Just do you have any question? Because for the internet, the guy in video, maybe we have to do the thing. I don't know, honestly, we don't. If it's just small question, we don't care, I suppose. Ouais.
Sinon, tu mets l'écran et puis on le remet à.
Tout le monde laisse s'asseoir sinon?
Ouais, tu mets une next presentation. Ouais, ouais.
Okay, yeah. You have a question?
Maybe demonstrate or tell something about
With
controllers that
the control board? Do we have? Yeah. Virtual analog? Non, mais tu peux câble bien. Yeah, I can. I just hope now.
We're gonna have the last session of the day with folks from Bella, who came all the way from the UK and from Germany just for us. So, is it Aiden or Adan?
It's actually Adan.
Adan, sorry. Okay.
It's alright. I mean, I live in the UK, so no one really gets
Yeah.
right.
How do they say in the UK? Like Aiden or?
Aiden or Anam, like no one actually.
Okay. Okay, so Adan. Okay, so Adan and Clemens from Bella, and yeah, this is gonna be the last workshop of the day. So enjoy.
Hi everyone. I'm sorry to disappoint you. We're not going to play with FPGAs now.
Wait. Oh, microphone.
I mean, I'm Spanish, so I'm naturally loud. I guess the recording is not like that.
Okay, I can take care of it. Just
Okay.
okay.
Sorry for the rest of the Spanish in the room for that statement. So yeah, I don't know. Like, for those that this is it's a little bit of an interactive workshop. We start by introducing a little bit the C++ API. but the idea is that you actually get to play with it if you brought a laptop in. If not, I would suggest that you team up with someone that brought a laptop. You need 2 USB ports because we are going to use a driver, and that needs extra power. But if you don't have an extra USB port, I also brought a power USB hub. So you're welcome to grab one. Like Clemens can give. We actually have 9, I think, because I brought one. Yeah. So yeah, I mean, shall I start introducing the workshop? So, I mean, you've been to the talk this morning, so most of the stuff that's here is probably. Yeah, if you want one, go and grab it. So this is what we do. This is Bella. That's the. Yeah, this is the small sister of the big Bella that you're going to be playing with today. That's kind of the original one based on the Beagle Bone Black. We did this small one, which is the Bella Mini, based on the Pocket Beagle, and we hope to have new Bellas to show hopefully soon. But in the meantime, I'll show you a little bit how we design our workflow for C++. You can also use Faust for Bella. You can use pure data. You could use Super Collider. You can we kind of pride ourselves on saying that Bella is polyglot, and that this is actually thanks to the people from Faust that also kind of work with us on the integration. Some people that also are Super Collider coders and work with us, etc., etc. But today we are going to do C++ just because the workflow is quite straightforward. It's the kind of default API on Bella. If you work, for example, pure data, it will work with libpd, and then you will have some C++ running as well, and there's a C++ wrapper. So, oops, sorry. So C++ is the default, right? Okay. So the board that you have in front of you, or if you don't have it in front of you, is this one. It comes with a few of the things that I mentioned this morning. You have analog inputs and analog outputs, digital I/O, stereo audio in and out, all of them jitter-free and aligned, the sample line. And it also comes with a nifty, I think it's 1-watt amplifier speaker, and peripherals like I2C, etc., etc. I2C is broken out there for convenience on an all MOL SKK254 connector. I mean, these details. But yeah, today we're going to actually use the stereo input at the end of the workshop. We're going to use the stereo speakers, but we're not going to use any of the digital IOs nor the analog inputs and outputs. Instead, we are going to use the sensor that is connected, that is on your board and on mine, which is also part of our design and things that we created to bring capacitive sensing basically to the maker community. And it's an I2C sensor that has. Sorry, I'm just going to go to the sensor first, and then I'll come back. Yeah, that's the sensor. So this is what we call a twill bar. So it allows you to track movement based on capacitive sensing on one dimension. You can have up to 5 touches. You can measure the contact surface that you're touching, and you can use that to create interactions. In this case, we are going to use that as a driver for interaction, for generating haptics and also some fun sounds that Clemens programmed for us today. Okay. So if you have your board, you should have 2 USB cables. You should connect both to your computer. One is going to be the standard USB cable that is going to have all the communication. It's going to serve the IDE on your browser, etc., etc. The other one is just for powering the drivers. Normally, you just need one, unless you want to use the drivers. You need a little bit extra juice that you can jumper around things and try to see if you can get enough power from one single USB. But I don't want to. Yeah, let's try not to reboot anyone's computer, or at least anyone's USB drivers. Okay, so once you're in, you can go in a browser. Firefox, Chrome, they work. Edge, if someone has that installed. And once you're in the browser, you can basically access Bella for programming. So you plug Bella onto your computer, launch the browser, wait a little bit for the IDE to be served, and you can access it on these different addresses. If you're on macOS or Linux, Bella.local should work by default. If you're on Windows 10, the IP is 192.168.6.2. Everything else 190.168.7.2. And if anyone has any problem with that, now is the time to raise your hand, and I will give you a hand with that. And you also, yeah, and as I said, you need the USB to barrel cable just to power the drivers. I'll leave that one on for a little bit, and then you can connect the boards and go on. Okay.
Will it work the same if you were to plug an Ethernet cable directly or in a local network?
It should work. Yeah, it should work on the with Ethernet on the local network.
Put an Ethernet from the server.
It will. The thing. I don't. It wouldn't serve the ID. Yeah. Actually, I think it should. Yeah, I think you should be able to access the ID on Ethernet. I haven't tried. Like last time I used Ethernet on this board was before that. Before the ID was even a thing. But yeah, definitely. Like the Ethernet peripheral is available, and you can use that over network. Yeah. Some people have used it, not myself actually. But yeah. Is anyone able to access the ID? All working? Good. Okay. Okay, I'll move. If anyone else has any trouble, Clemens is going to be around for the first bit, and then I'll be around for the second bit. Okay, so if you open the IDE, you see that you can there's a code editor in there with some code probably showing, and then a few things down the side. We have a range of examples that one can try in different languages, most of them in C++. You have a tab where you can actually look at the files on your project and add new files or edit the project or download it or delete it if you got bored of it. There's another tab on which you can set the settings on the board. That's the hardware settings, ranging from the block size, the number of analog channels that you want to use if you were using analog channels, the sample rate of the analog channels, which changes depending on how many channels you're using, headphone level, like the PGA, which is the programmable amplifier gain at the input, etc., etc. Those are settings that you can change. You also have settings for your specific project, which are compile flags, for example, that you might want to set, like for having like a more verbose output or like a faster performance, or a specific set of things. There's documentation for all of this. I'm not going to get into details. Hopefully, the settings, each project saves the settings, so they are not shared within projects. Each project has its own set of settings, and in this case, all of them should work by default. You should not have to change anything. But if you were using headphones, maybe you should try to tune the headphone output to your liking. Okay, then there's also the pin diagram, which is quite useful, which tells you which pins on the, because we break out a few of the pins from the Big Bomb Black, and then we also break out the ones that we use on Bella. So it's good to know which are which. I don't know if you can see it there, but you will surely be able to see it on the browser. You can know what function it is, where is the digital pin that I want to use, the analog outputs, analog inputs, even power and ground. So that's for whenever you're plugging things on the board and prototyping. As I said, in this case, unless there's little to no error, unless we plugged in the I2C wrong, and you'll know in a bit, and then it's easy to fix. Okay, so the API. I don't know. I said earlier that Bella works on Xenomai, and there's a callback that is called on Xenomai. But we also have the PRU aligning all the inputs and outputs and serving those to you. Of course, that's written, but there's an API that is exposed to the user that's much easier to use. So there's three main functions on the Bella API. One is the setup, where you do all your allocation, memory allocation, whatever you need to do. The other one is the cleanup, which is when you're done with your beautiful audio code, you get rid of all the garbage that you might have generated in the meantime. And the important one is the render, which is the one that is called by the audio callback synchronously. So this is an example of how to write a simple sign generator on the Bella render. We have the context variable, which gives us the important information about the state of the board in a sense, the context, like it gives us the number of audio inputs and outputs that are available, it gives us the sample rate, etc., the number of audio frames, and it also gives us access to the API. So this is passed, and you can also pass user data. If you were to wrap up this function somehow, you could pass the user data, or if you were to do another call to this function, you can pass extra data into that. But basically, everything that runs in here runs once per block. You have specified the block size on your Vela, and this runs one per block, right? Here we're iterating over the audio sample, so whatever is inside that for loop runs one per sample. So if you want to write a sample by sample code, you know that the latency, as I said earlier, is going to be twice the size of your of your block divided by the sample frequency. But everything that happens here happens in one sample cycles. If you do something here that takes, on average, longer than one sample to compute, you're going to screw up your deadlines. So you should perhaps think about doing it differently, which is what we're going to show later. So you see that we are generating the phase of a sound wave, we are wrapping up the phase, and then we are writing it to the output. And this runs one per channel. So you write, the audios and inputs are interleaved. You can write to them in an interleaved manner. You can write to them in a de-interleaved manner. It's a bit up to you, but there's this nice API function that allows you to write to this channel this output, which is probably what most people want to see, I hope. So you write on a specific frame, specific channel, and you write the value. This is already what I said. So setup runs once at the beginning, then you start the audio callback that is called repeatedly, and it's the one that gives you access to the buffer where all the inputs and outputs are ready for you, and the cleanup code. Okay, so today's theme of the workshop is about haptics and feedback. And I think it's something that you can achieve quite a lot of nice things with very little code. And then I thought, okay, let's do a run of that, and then I'll let you guys experiment. And the way we are achieving haptic feedback in this case is with a transducer, or with a driver that is at the bottom of your board that you will be able to see, and the 1 watt amp that's included on the Vela board. These have an audible range, so we can actually use them also to create auditory feedback, and that's the second part of the workshop today. But if you use them at low frequencies, you can generate nice feedback effects. Okay, this is a particular thing. So okay, the project that you should have open now should be called PAW00 driver test. And if you run it using this button, now we are going to get a lot of vibrating boards, hopefully, if everything is working. Yeah, that's one. So if you run it, you can go to the GUI. Actually, I'll do that. I'll do this myself. It's gonna be a fun one. Okay. Okay. So I'm going to show. I'm going to walk you through a few of the features that are available here. So that should be driving the actuator already for you at a specific frequency. I'm going to drive mine. I got the boards without screws, so mine is going to actually jump out of the board. That's mine. If you come here to this small tab, you can launch the GUI and change a few of the parameters there. So this is a GUI that is basically communicating to Vela through a WebSocket, so you're able to feed back back and forth information through the WebSocket. And in this case, we have these small sliders that we're using for control parameters. So this is called once per block, and it gathers the data from the GUI and it maps it to something. In this case, the frequency of the oscillator, the frequency of a modulator, and then, I mean, this is intended, so you could hook up headphones and listen to it. So there's a haptic amplitude for the haptic oscillator and amplitude for the audio oscillator. So yeah, I have mine. Mine will be like standard mobile phone ringing. It's time to wake up. Yeah. Okay. So I mean, this is just to make sure that your drivers are working. If they are not working, then we need to figure something else for the rest of the workshop. Okay. I don't know where I put my presentation. Oh, there you go. Okay, so those are the controls, as I said. About how the code is structured. We have that render call that is generating a few oscillators. It's wrapped up in a library so that you don't need to see all the phase wrapping and that sort of stuff. But basically the code that you can see on your render is that of generating the oscillators. But we are controlling the amplitude of those oscillators by means of the GUI. In this case, we have a few sliders that we have set up with our controller. This is our setup. This is where we say, okay, we want to add two sliders to this controller. And then on render, we are getting the value from those sliders once per block. It's as simple as that. There's a little bit of kind of WebSocket connection and handling on the library, but for prototyping, this is good enough. Okay, so we go back to Trillbar. Now we're gonna explore a little bit like a few kind of like haptic effects on the bar that we have there with the oscillator. So as I said, this allows us to track movement in one direction, up to 5 touches. In most cases, we're just going to use 1 touch for this purpose. But we're going to use simple audio modulation techniques to create haptic sensations. That's the trill bar on your board. And here's where things get interesting. The trill bar is an I2C device. And today I talk a lot about the importance of sampling sensors together with audio at audio rate, and having the render callback that is kind of like a real-time guaranteed. But I2C is not real-time guaranteed, right? But we still want to be able to communicate with that. How do we do that? Xenomite has a primary mode on which it runs our audio code that has higher priority than anything else in our system. But we also can run Linux process at lower priority. So what we're going to do now is going to create an auxiliary task, which is going to run a lower priority than our audio thread, that is going to gather the data from the I2C, wrap it up nicely, and then we should be able to use it on a render call. Of course, if you are not careful with the kind of with how you handle this data, you're going to notice jitter as part of the interaction, right? Because this runs whenever your audio callback is finished. So it's not gonna be sample aligned. So in this case, we create an auxiliary task, which is an infinite loop that runs whenever the audio callback gives some space, and it's gonna gather the data from the I2C and package it up for us. So this is what goes on setup, and this is a little bit what happens in the loop. So there's a loop that says, while Bella is still running, do some stuff, and then sleep for a little bit for a predefined time. But this is what's happening in the thread that runs at the lower priority, in the kernel thread. Okay. So yeah, in setup, of course, we are not going to show the whole I2C handling in this case. We wrote a nice library for the touch sensors on which you can set the address, the type of sensors, and then just use it to read the locations on the sensors, read the number of touches on the sensors, and then for whenever you make a touch, store the location of the touch and the size of the touch in an array. And then that array is going to be accessible by both threads, so that you write to the array on this thread and then read from the array on the audio thread. As simple as that. The first example that we have is a little bit of a visual example, just to give you an idea of how the trill sensor works. So if you want to go onto, I'll do it here. If you want to go into projects, there should be one called Trill Visual. And if you run that one, it's going to take a while to compile. That's the thing, we are compiling. The nice thing about the toolchain is that it's self-contained. So it serves the files through the IDE. You can edit the files. You can do all the things that we're going to do through the IDE, but then it also compiles on the board. So it takes a little bit longer to compile that we're getting into your laptop. You can do distributed compiling if you want. There's ways to set that up. But for today, I thought this would be enough. So if we come here and then come to this, to the GUI, where we had the sliders before, we'll have a representation of our trill bar. And then if you have several touches on the trill bar, you can see the location, the size of the touch changing, and then up up to 5 touches. These don't come in they don't come in a specific order, but you kind of like, you can see how reactive it is. I mean, this should work every 5 nanoseconds, so on. But as I said, it doesn't matter what's the latency of your I2C transaction, since it happens at a lower priority thread. Jitter might be a thing that you need to take into account. Hopefully not for these applications, but you can tell me at the end of the workshop. Okay. So everyone got to try that? Works for you? Okay, so your trills are working, that's good. That means that we write the I2C the proper way around. If you wanna interact with it and see how it sounds, you can run the trill, PAW01 trill sound, which uses the size and the touch to modulate a few oscillators. This is one of these examples on which having a really simple generator but rich interaction could go a long way. You can, like, can I zoom in? The resolution is fixed so that it can be streamed. Oh, like that? Yeah, there you go. So now we have an orchestra of sine waves that you can control with your fingers. And now I'll let you decide how reactive that is. It's leave it up to you. For me, it's quite fun, even though it's just a few oscillators. But yeah. Okay. Yeah. In the well, actually, this should be the second one. Well, anyhow. Okay. So if you're ready after making a few weird sounds, we can try haptics now. So there's the first example that I have on haptics is basically it will trigger the driver for a few milliseconds at low frequency whenever there's a new touch on the board, and then the vibration frequency is going to be a scale on the number of touches. So if you have one touch, it's going to be a lower frequency. The more touches that you have, the higher the frequency is going to be. And this is a little bit to explore how you can create different sensations at different frequencies. So as you see, I have the number of active touches that I gather from my non-audio thread, and I'm mapping the frequency from 0 to the number of touches to a range of frequencies that I set up in there. And then I have an oscillator, which is like I think in this case it's a simple, it may be a sawtooth oscillator. I need to check that, but it says the frequency based on that. Okay. So if you try that one, PAW0 do trill A, you should no longer hear the board. I mean, you can hear it rattling, but you should no longer hear the oscillators. But now you should feel that every time you touch the board, there's, oh, mine is still with them. There's a haptic sensation program for you, if it builds. Yeah, there you go. So if you add one touch, it will react to it as a haptic button would do. If you add more than one touch, like, the frequency will change. Oh yeah, yeah, and the screws might pop out of the board. Sorry, that's because I travel with this on the plane. Okay. Okay, but this is, I mean, like having a Linux microcomputer to trigger a few haptics is fun, but it doesn't get a long way. Let's try to make it a little bit more interesting. With the second one, I'm going to try to build to a small simulation that I did with really simple tools of surface roughness. So the first thing that we're going to do is we're going to map the touch size to the amplitude of the oscillator that generates the feedback. If you touch it slightly, then it should generate a small vibration. If you touch it with your whole finger, it will generate a bigger one. So if you go to PAW02 trill B, that should be the second one. Okay. So you can see now it's like now the driver is going to stay on when you touch it, but then if you touch it with a little bit of your finger, it's gonna vibrate with certain amplitude. If you put your whole finger on top of it, it's gonna go a little bit more intense. Okay, And then if you move your finger across the surface, you will see that the amount of touch that you put on top of the trill bar, together with this simple interaction, already creates a different sensation, right? Like a different sensation on how the surface behaves. Let's try to do something a little bit more interesting then. What if we just modulate the amplitude of this oscillator? We have a second oscillator that, based on the amount of touch, generates modulation, an AM modulation on top. So this is actually this is what I just did. Sorry, this one. Sorry, trill bar C builds a little bit on top of that. The idea is that now we are gonna map the touch location to the frequency of the oscillator instead of the amplitude. The amplitude is still gonna be mapped to the amount of touch that you put. But in this case, instead of taking just the position or the amount, we are going to look at the velocity. We're going to look at how, and this is quite interesting. We can dig into the code lately. How do you compute the velocity of something that doesn't happen at all your thread, right? You need to get the last readings that you had before, so start from the previous readings. But what's your clock? How do you update that? It's easy to do, but it's a little bit interesting how you need to change your mindset just to do that. But in this case, basically, we are taking the velocity of the movement across the slider, and we are mapping that to the amplitude of the haptic oscillator. Which means that if you touch it slightly, it should be quite smooth. If you dig into it a little bit more, it should generate like a harder sensation of roughness. I don't know if that. I mean, this is me. This is not scientific at all. This was me trying to figure out a few nice interactions. So if you don't think it simulates roughness at all, then tell me. Okay, still building mine. Sorry. So the idea with this is, I mean, we introduced how to use trill in a non-priority thread. We showcased how to do really simple haptic interactions with audio modulation objects and really kind of like simple concepts, and try to do something interesting with it. What we're going to do now is we're going to create a really nuanced instrument with some code that Max put together, trying to use the same resources that we've been exploring. So now we're gonna create a feedback machine. Is that the plan? Should I take over? Yeah. Do you want to use my laptop? Are you okay with that? Yeah. Yes, I need your mic. Oh, yeah. Sure. I'll set this one up for you. Sorry, people that are online. How's that? This one.
Okay. People can hear me. Okay, so where are we? Where are the slides? No?
Oh, you can slide to this.
Ah, here. So, as another application, we thought we do feedback, right? We have a little piezo under the baler. Maybe you spotted that already. And it's kind of directly on top of the driver, and you'll be like, oh, feedback, right? So we can feed the driver signal back through the piezo into our baler code. And I prepared a little bit of an environment to do physical models. It's a mass interaction model there. So you can connect these little masses through springs and dampers and build, for example, a plate or a string. So there are some macros to do this, but you could also go and create your own little network of springs and dampers and resonate them within the feedback loop. That was the idea.
most of the time it just screeches and does very unmusical, scary sounds, but that's the idea here. Not sure how musical valuable this will be, but let's just try it out. So you guessed it, it's that piece of code here. And I'm not sure if you can see that. Yeah, that's. Yeah, I can hear some feedback there already. Nice. Okay. So you can see in the code, we're using this coupled oscillators library here, and these need a configuration. Right? We can put a configuration. For example, we can put a macro to generate a string with the oscillators, or we can put a macro to generate a plate. And then within the code, we can do a few things, right? We can put our audio input into the model, and then take the output of that and put it onto the driver, right? You can see this further down. And this really sounds nice. Wow, that's it's from them. It's from the. No, that's meant to be sounding like this. That's on purpose. Okay. Maybe let's stop for a while. I just want to add some more words to this, and then you can experiment until the ears bleed. So just to explain the code and what possibilities you have to experiment, and to say this is, when you scroll down on line, what's that, 103, this is where you actually feed the model with the audio stream, line 103. There you have the audio input from the piezo, that's in, right? And then that generates the audio output here, the variable out, right? So that's where the model feeds through. And here you have a mapping, and that might be interesting. This is the mapping of the touch position of the slider that maps to a string model right now. So what we are actually doing is we are changing the output position of the model with the slider. So we are listening different points of the string, of the virtual string, depending on where we put the finger on the slider. So and if you listen closely, you hear different overtones of the string at different positions, because it will feed back at this overtones, right? So if we made the string longer, for example, you could put a different size here in the constructor, in the configuration. So if you remember, I think 64 notes could also work, so you would have a deeper resonance maybe. I didn't try this yet, so it might be worth trying. And also if you increase the stiffness, the sound will be higher, right? Also, the more notes you put on, the more realistically will it sound like a string, because it's a very rough approximation of a string if you just put 32 masses on in a physical model. So the more notes you have, the more it will sound like a string. Less stiffness will sound lower. And if you change the model to a plate, you have a richer sound as well. Like you can, if you have a bigger model, I think 8x8 is the biggest size that we can calculate on the Bela right now. So 64 notes, that will almost sound like a gong type of thing. So if you want to try that, just use the plate configuration for here in the constructor. Just exchange string conf against plate conf, and then you should have different resonance behavior, and maybe you could also hear the actual plate resonating. It might be interesting to try.
No, you can rebuild
if it's run and you just change the code and you save it, it's better.
and you save it, it will. I mean, in this case, it will recompile. There's no saving option. It's automatically saving it as well. But if you compile it, with the whole thing, yes.
Okay. Some strange component.
I think maybe this is the one that I sent Clemens. So maybe let's see. I have another.
Ah, it's okay.
No, I have another board.
I can do noise too, so maybe this one. Yeah, maybe the center.
So mine is still building.
Still building?
I'm building the plate model, so let's see if that. Okay.
Not working for you? Okay, let me see. I'll bring one of these just in case.
So, and if you wanted to, you could actually initialize an empty model and then do that manually by adding springs, right? And the way you do this is you call this function here, add spring, and then you first you have to tell the size of the model that's empty, right? The amount of nodes that you have. So here in this case 3 nodes, and then you add springs between the nodes. In this case you can add up to 3 springs between 3 nodes, right? 1, 2, 3 springs. And you have to connect them between, you have to give it the left and the right node number. So this would be 0 and 1 maybe. And then the stiffness of that spring. So you could build up your own little models. And also take note that the amount of overtones a model generates is dependent on how many masses you have. So if you have 3 masses only, it's only 3 kind of like 3 sine wave oscillators. So the more nodes you have, the more overtones it would generate. But yeah, that's and of course you have to add a wall, because if there's no node that is referenced to kind of a 0, to kind of a no wall that keeps them oscillating, right? You need to have a pushback force at some point in the system. So this you will do with this code, add wall, and then you just tell it on which node you want to have the wall. And you also need to have so this connects a wall through another spring to the node. But yeah, that's it basically. If you're having fun with this, you can continue a little bit. And I guess then we are ready for the party. Are we?
I hope it was clear. We tried to showcase the API, give you something interesting that is simple. You can play with it for as long as you want, as long as we are able to stay here and change things, and let me know if you have any problem with it. But you can also you can also ask as many questions as you might as many questions as you might want, or if you are a Vela user or you have used Vela before, you can ask them to actually put in some requests. If you want. There's I put there a few examples about instruments that have been built taking feedback and haptics into into account. There are our blog posts. The slides, these are actually not pushed into GitHub. The ones from this morning and the examples are on GitHub, so those are easily accessible. I'll leave the GitHub link there so that you guys can have it, and I'll send it to Roman so that he can forward it for whoever wants to see it. And yeah, this is pretty much it for today. Good, thank you. Together with the GitHub.
everyone. Just to wrap it up, thank you for all coming. Thanks to the presenters. And yeah, well, you can stick around until 7 or something like this. At 7, presenters were, like I told you, like we're all going downtown, right, like to a restaurant. So, we all sort of have to leave by 7. Okay, so like you're welcome to stick around until 7, but after that, everyone should be out. So, anyway, thank you very much, and see you next time.